So we learn how to calculate eigenvalues or find eigenvalues, real eigenvalues of a matrix, computationally. We want to do some more, I guess, theorems, some theoretical results that are really important, that come from the characteristic polynomial, the characteristic equation. So here's our first theorem. This is a really handy one. It says this. So it has to do with triangular matrices. If A is an n by n triangular matrix, then its diagonal entries, I should say descending diagonal entries, are its eigenvalues, are its. Okay, I'm not going to prove the whole theorem. I'm going to prove half of the theorem. I'm going to prove it just for upper triangular. You can do the same thing for lower triangular. So here's a proof just for upper triangular matrices proof. So I'll call it a partial proof. It's not really a full proof, but it's sufficient, right? Suppose A is an n by n. We'll just look at the upper triangular case. If you want to do the lower triangular case, you can. N by n upper triangular matrix. Right? That means, what does that mean? That looks like what A is of the form A11, A12, dot, dot, dot. A1n, and down here you have 0, and then A22, dot, 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 A2n, dot, dot, dot. You got a bunch of zeros down there, dot, dot, dot. You got a bunch of zeros down there, dot, dot, dot. A bunch of zeros, and all of a sudden, dot, 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 down the diagonal, you got A, N, N, and dot, dot, dot. So it's an upper triangular matrix. So you got zeros below the main descending diagonal. All right, so we want to focus on the eigenvalues of these guys. So what do eigenvalues look like? So lambda is going to be an eigenvalue of A. We know this result if and only if the determinant of A minus lambda I equals 0. In other words, the characteristic polynomial evaluated at lambda gives you 0. That's the same as, okay, let's take the determinant of this A minus lambda I matrix, set equal to 0. That means I'm going to take my diagonal entries, right? I'm going to take these guys. I'm going to subtract the lambda from them. Right? I'm going to have A11 minus lambda, A22 minus lambda, and so on and so forth down the diagonal. ANN minus lambda. Right, we have an n by n matrix, so our diagonal in the corner there is ANN. And then we subtract lambda. And then everything else is going to be the same, right? We're going to have what? A12, and so on and so forth. A1n, and then here so on and so forth. A2n, and then going down, so on and so forth. All right, below the first entry in the first row, first column, we're going to have a bunch of zeros, dot, 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 zeros. And then you got zeros below the second column, and then dot, dot, dot over, like that. Okay. So, going down, scrolling down. So what happens when you take the determinant of an upper triangular matrix, right? This is still upper triangular. Nothing has changed. It's still upper triangular. But when you take the determinant of an upper triangular matrix, any kind of triangular matrix, you're just going to have what? The diagonal entries multiply the product of the diagonals. A11 times lambda, A22 times A11 minus lambda, A22 minus lambda, so on and so forth. ANN minus lambda, and that's all equal to 0. So this is equivalent to saying, well, if you have this product of entries equal to 0, then that forces lambda to be A11. Lambda also could be A22, and so on and so forth. Lambda could be A and N. Can be none of those. So lambda has to be at least one of those. So that's it, right? We've proven it. I don't really need to put a box, right? I have this habit of putting a box around this. That's the end of the proof. What have we just proven? We've proven that lambda is an eigenvalue if and only if it's a diagonal entry, right? And this is for a triangular matrix. So if A is an n by n triangular matrix, then its descending diagonal entries are its eigenvalues. Yeah, that was what we were proving. The eigenvalues are A11, A22, through A and n, right? The diagonal entries. Right? Eigenvalues consist of just A11, A22, through A and n, right? Diagonal entries. Big result. All right. That's half of the proof, right? Because we just did upper triangular. You can do lower triangular. Okay, here's another big result. Call it a theorem. It's pretty big. An n by n matrix, you have to be done with the square matrix, is singular, means not invertible, if and only if lambda equals 0 is an eigenvalue of A, is an eigenvalue. Eigenvalue. Okay. So matrix is singular if and only if 0 is an eigenvalue of A. That's actually really simple to prove. Proof. So let's let A be an n by n matrix. Let A be an n by n matrix. That means a square matrix. Same number of rows as columns. So lambda equals 0 is an eigenvalue of A. That's what we're going to start with. That's equivalent to saying what? Determinant of A minus, rather than putting a lambda there, I'm going to put a 0 there. I'm going to let my lambda be equal to 0. Determinant of A minus 0 times the identity equals 0. So normally we say what? Determinant of A minus lambda I equals 0. Here I'm letting lambda be 0, right? Because 0 is supposed to be an eigenvalue. Now what does this do? This is equivalent to, well, 0 times the identity is the 0 matrix. So you're going to have determinant of A minus, this is the 0 matrix, right? Equals 0. Scroll down. But wait a second. Determinant of A minus the 0 matrix. A minus the 0 matrix is A. Wait a second. Determinant of A is 0. That means what? A is singular. Remember, a matrix is singular if and only if it's determinant of 0. It's invertible if the determinant is not 0, but it's singular when the determinant is 0. That means it's not invertible. There we go. So singular matrices have 0 eigenvalues. Non-singular matrices would therefore have non-zero eigenvalues. So if you ever have a 0 eigenvalue, that means you have a non-invertible matrix. Non-invertible matrix, singular matrix. All right, what else? Here's a big result. Not hard to prove. So they made a big fuss about this in the previous section, but I don't think it was appropriate to prove it in the previous section. This is about A and A transposed. So let A be an n by n matrix. A and A transpose have the same eigenvalue. So they stated that, and they actually tried to get us to prove it in the previous section. I think it was very inappropriate, though. It's best for this section. Have the same eigenvalues. So every matrix, every n by n matrix, every square matrix and its transpose will have the same exact eigenvalues. Let's prove this. So in the background, let A be an n by n matrix. So lambda is an eigenvalue of A if and only if what? Determinant of A minus lambda I equals 0, right? Determinant of A minus lambda I equals 0. But wait a second. I don't know if you remember, but when we did determinants, we said that every matrix, its determinant is the same as its transpose. So determinant of A minus lambda in is the same as the determinant of A minus lambda in transposed. This is something we actually did not prove, that transposes and the original matrices have the same determinants. We said it would require induction to prove it, and we don't get into induction in this class. That's for, it's more proofy. Now, if you remember properties of transpose, we did prove the properties of the transpose way back when we introduced the transpose, way back in probably like late January, early February. The transpose distributes over top of addition or subtraction. So this is going to be what? A transposed minus lambda in transposed. All right, so we got what? Determinant of A transpose. Think about lambda in. Lambda in is basically the identity matrix with, rather than ones down the main diagonal, you have lambda. So when you transpose that, you're going to still get just lambdas down the main diagonal. So that's just the same thing as lambda in. So what do we have here? We have that the determinant of A transpose minus lambda is 0. Well, this is just a fancy way of saying that, what? Lambda is an eigenvalue of A transposed, right? A transposed. Before we had A up here, right? Now we have A transpose kind of in its stead. And that's the proof. We have that lambda is an eigenvalue of A if and only if lambda is an eigenvalue of A transposed. You think we should stop there? Or should we just squeeze something in? I think we'll probably stop there. Okay. So the big results here that we have is triangular matrices. Their eigenvalues are just their diagonal entries. The other result we have is that singular matrices have 0 eigenvalues, and matrices with 0 eigenvalues are singular. That means they're not invertible. And then we have that A and A transpose will always have the exact same eigenvalues.